So this is lesson 10.8 on Florin and Taylor series. So in lesson 10.7, we talked about how to make our series, our power series, into a function, right? So what we're doing now is backwards. We're going to take our functions and rewrite it into a series. So Maclaurin was actually the first one to start this. He started writing these functions into series. And we talked about the fact that really it's because back in the days they didn't have calculators. And this is also actually the basis of our calculator, how our calculators are able to crunch these numbers out for us. So we're able to find like e to a number, like e to the power of 2, or e cubed, or sine of 37 degrees, of course, in radians. But this is how the calculator is able to give you all that decimal in terms of your answer, because of these power series that gets rewritten, of these functions getting rewritten as a power series and breaking up those numbers and breaking up these terms, and then you get some accuracy with it, right? So Maclaurin discovered this, and of course then Taylor kind of jumped on and expanded it more. So for a Maclaurin series, your C is 0. You're centered at around 0. Whereas a Taylor series, you have a constant, so you're centered around x minus c. So it's kind of referring to that radius of convergence like we did a couple lessons ago, okay? So the focus of today is going to show you how to set up a Maclaurin series for some of the functions that we have here. We're going to start with something that we do know, and so that way it kind of supports the idea of how the series works and how it is effective. And then we're going to venture into something that is a little bit tricky. In the next lesson, we'll talk about how to write a Taylor series. But again, the only difference between Maclaurin and the Taylor is mainly here, where you have, you're taking the derivative. So Maclaurin says you take the derivative of each of your function each time. So these are derivatives. And you plug in 0, and you multiply it by x, you multiply by the power series, so x to the n power over n factorial. Whereas Taylor says, all right, well then I have a constant, so I'm plugging in c instead of 0. And instead of x, you have x minus c in terms of where the variables are going to be, okay? All right, so the setup of this is quite similar, well, quite simple actually. So what you're trying to do is you're trying to start off with a few of the n terms, and then you try to generalize, give a formula for the general idea. So for the function f of x equals e to the x, we set up this chart, not a t-table, but a chart, because there's a couple of columns here. So you set up your n, and then you start at 0, because that's where your summation, your sigma, usually starts at n equals 0, right? And these are discrete, so n equals 1, 2, 3, and then so on. And you want to generalize and get an n at the end. Now, you have the power to expand this or, shrink it if you want, but typically you need at least 1 or 2 or 3 of these to really see a pattern. If you need more to see the pattern, then of course build this chart to be a little bit longer. So, make sure you put in n equals 1, 2, 3, 4, 5, 6, even up to 10 if you need to see the pattern. If you already can generalize it within the first few terms, you don't need to go on, okay? All right, the next column, we take the derivative, so the nth derivative of my function, right? So my equation is e to the x. Well, the 0 derivative is the original function, so it's just e to the x. Now this is actually quite easy, because e to the x, for every iteration of its derivative, it's exactly the same. So it's going to be e to the x, e to the x, e to the x, e to the x. All right. Next, Maclaurin says you then plug in 0. Well, this one's nice. Either 0 or 1. So it's just 1 all the way through 1. Now, keep in mind, sometimes, okay, we got very lucky. This one we can't. Sometimes you're not able to generalize here, right? And maybe it's easier to generalize here. And sometimes you can't even generalize here. It's most important to generalize in the third column here. If you can generalize in the third column, that's your ultimate goal. So again, you don't have to try super hard to make sure you can generalize in every single column. It is most important to have the generalization at the very, very end. Okay, so this is what we're looking at. Then Maclaurin says, take your derivative, now multiply it by x to the n over n factorial. And that's what he discovered. This is his contribution, right? So this is the new idea where you multiply this by this power series. So then this is going to be, well, just 1 times x to the n, or x to the 0 over 0 factorial. Shockingly, 0 factorial is 1, so this is a term of 1, right? Then you have 1 times x to the 1 over 1 factorial. This is x. And then you get 1 times x squared over 2 factorial, x squared over 2 factorial. And you can see it's x cubed over 3 factorial, right? This is why we need a few, because the first two doesn't really show me a pattern, but by the fourth one, I can see the pattern. So yes, this is indeed x to the n over n factorial, right, times 1, but you really don't need to put the 1. So the function e to the x can be rewritten as a summation, right, a power series of x to the n over n factorial. So what does this mean? It means that, well, back in the days, if the mathematician wants to find e cubed, right? So, and within a certain number of decimal places, then that kind of determines how many terms you're adding up. If let's say I want to find e cubed, then I just expand it out, because I know e to the x is equal to 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24, and so on, right? But if I only need that much accuracy, I can stop here. E cubed means 1 plus 3 squared over 2 plus 3 cubed over 6 plus 3 to the fourth over 24, and sorry, terrible writing, and so on. If I want more accuracy, I add more terms, right? So this is how your calculator actually crunches out the number for e cubed, right? So it's kind of cool. All right, try the next one. We have our f of x equals 1 over 1 plus x, okay? So same setup. We start with my n, make my chart, 0, 1, 2, 3, and then eventually generalize, right? Okay, so f to the nth degree of x. So because I am writing this, I'm trying to use this as a, I'm trying to take the derivative of the function. So then rewriting it as 1 plus x to negative 1 may be more helpful than leaving it in this original form of 1 over 1 plus x. But it's kind of your choice, right? So I'm going to write both, right? So I'm going to have an or here, because I do need it in terms of a power to easily take the derivative. However, it's much easier to detect, in my opinion, much easier to detect the pattern if I leave it as a fraction, as a rational expression here. So you have 1 over 1 plus x, which is really 1 plus x to the negative 1. Take the derivative, I get negative 1 plus x to the negative 2, which is negative 1 over 1 plus x squared. Then you have 2, 1 plus x to the negative 3. So 2 over 1 plus x cubed. And then you have negative 6, 1 plus x to negative 4. So negative 6 over 1 plus x to the fourth. Okay, so let's see if we can generalize this. First of all, I see that, oh, my signs are alternating. Starts positive, negative, positive, negative, positive, negative. That gives me a hint that's negative 1. Now, is it to the n or n plus 1? If it's to the n, it starts at 0. Negative 1 to 0 power, that truly gives me a positive 1. So great, I don't need to change anything. If I want a negative to start, maybe I need to start at n minus 1 or n plus 1. So you have to adjust that power to match your pattern here. Okay, then what I see is I have a 1 on top, so that doesn't matter. Actually, one for the previous couple. So the coefficient is going to be different. But I do see at the bottom is 1 plus x. And I also see that the power here is always 1 more than my n number here. So that gives me, this is n plus 1 here. So last thing I need to deal with is the coefficient, right? So what is my coefficient? I have 1, 1, and I'm not looking at the negative because I already took care of the negative with the alternating negative 1s, right? So I'm looking at just the numbers here. So I have 1, 1, I have 2, I have 6, and the next one I didn't write it out, but next one will be 24. So that you should recognize eventually that is n factorial on the top. Okay. All right. Again, it's not super important that you get your generalization in this column, but it's more important in the next column. So make sure you can do it in the next column. Okay. Sorry, my camera's having some issues there, but no big deal. All right. Next column, I am going to McLaurin says plug in 0. Right. All right. So when I plug in 0, this one's actually pretty nice. I get 1. Plug in 0, I get negative 1, 2, 6, 24. So you realize that your denominator, because you're plugging in 0, your denominator here, 1 plus x, is going to turn into 1. So that's gone. So you're left with just, first of all, it's still alternating. So I forgot my negative 6 here, sorry. So it's going to be negative 1 to the n times n factorial. My denominator is gone. I don't need to write that 1, right? And then lastly, you need to take your column here and multiply it by x to the n over n factorial, right? And you don't need to write it all out, but it's not bad practice because it's going to be very useful in the next lesson if you write all these things out. So this is 1, this is negative 1 times x. This is 2 times x squared over 2 factorial, which is just x squared. You have negative 6 times x cubed over 3 factorial. which is negative x cubed, right? So what does that do? Well, that takes my coefficient from the previous column, multiply it by x to the n over n factorial, and I clean this up. So I would get just negative 1 to the n, x to the n power, right? So again, if I were to rewrite this, my function of 1 over 1 plus x can now be rewritten as a power series n equals 0 to infinity of negative 1 to the n, x to the n, okay? And yeah, so this is the same usage as what we did before. Again, if you want to look at manipulations, so let's say I change this x into, oops, sorry, I didn't mean to do that. I change this x into 2x, then all you do is plug in 2x into this function. That will give you a new power series, so you don't have to redo the whole thing again, okay? All right, last one is a function of sine. So you have f of x equals sine of x. So this one has a little bit more work. So what I'm saying is when you're making your chart, make it a little bit bigger. 1, 2, 3, 4, 5. It does take a little bit more on this one to see the pattern, okay? All right, nth derivative of x, right? So you start with sine x, and then when you take the derivative of sine x, it gives you cosine x. Take the derivative of that, you get negative sine x, and then negative cosine x. Then back to sine x again, and then cosine x. So you can see the pattern repeats itself after 4 iterations. So really, you can't generalize here. There's no generalization of this pattern because there's not really a true pattern. You could talk about this pattern in terms of 2 sets of patterns, but that's not important until later on. So for this one, you really don't need to. So remember, I said that it's not really crucial that you get the generalized term for this column. Let's see about the next column, okay? So f of n of 0. So Maclaurin says plug in 0. Sine of 0 is nice. Sine of 0 is 0. Cosine of 0 is 1. You get 0, negative 1, 0, 1. Again, I still can't really generalize here because I see 0 every other one, but then the 1 has a sign change in between. So still hard to generalize. Okay, so now you take your pattern, multiply it by x to the n over n factorial. Okay, the first one will give me 0, so you really don't need anything there. You can put 0, you just, cross it out because there's nothing there. It's 0, nothing there, okay? Next one, you have 1 times x to the 1 over 1 factorial, which is just x. Okay, I got 0 again. I get negative 1 times x cubed over 3 factorial, so negative x cubed over 3 factorial, nothing here. 1 times x to the 5 over 5 factorial, so x to the 5 over 5 factorial. Okay, so what you need to do is you need to take these numbers down and don't include a 0 because there's no point in including zeros. Zeros are not even placeholders, right? If you actually compress this into a new series, you will see that your pattern is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And you can guess the next one, right? It's going to be minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial, and then so on and so forth. All right, so now using the idea of this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. That will make it a lot easier for you to generalize your pattern here. All right, so first thing, I see that it's still alternating, right? Again, you don't even need the 0. The zeros aren't important for us now. So zeros are gone, and now this is the pattern I have. Okay, so then to rewrite this summation, this new power series is going to be negative 1 to the n power because I'm still alternating my positive negative signs. Then I take a look, right? It's hard to see with the first term, but I can see with the next terms, right? So if you have your powers here, first of all, the power and the factorials match. That's awesome. Then I look at the power and see how does that connect to my n. And I see that it is going to be double my n, but minus 1, right? So 2n minus 1. So double your n minus 1 will give me my power. So it'll be x to 2n minus 1. And then all over 2n minus 1 factorial, right? Because they are the same thing. So just double checking. Oh, plus 1, sorry. No, minus 1 plus 1. Plus 1, yeah. 2n minus 1 give me 1 number less. All right, so that is your power function, power series for f of x equals sine of x. All right, so if you have time, try this out yourself because you'll see if you're doing cosine of x, since sine of x are the odd powers, your cosine actually has very similar behavior. It's still alternating, still have an x over something factorial, but now it's just the even power. So it's 2n and over 2n factorial. Okay, all right, that's it for this one.